Hi, welcome along to our third little video podcast in the set about emission spectra and line spectra. We'll look at the fluorescent tube now, which is a kind of application of all the knowledge that we've met so far. Just a sort of trendy light fitting here. I'm going to show you this hideous device here. Now, it's possible that some of you are a bit more committed to this than me, but apparently that's a tanning booth. And not only is it not a device of medieval torture, apparently you can pay to go inside one. It's kind of hard to imagine. What we're looking at though is loads and loads of those tubes, which illuminate classrooms, offices, homes all around the country. But actually what they're lacking here is the fluorescent part. And their tubes just giving out ultraviolet light, hence the way that the device can give you skin cancer, and I suppose a tan as well. We'll be looking at kind of why we use those tubes, why they're giving out ultraviolet light, and how comes they're made safe in the rooms that are around us. Right, what we're looking at here, we've got a fluorescent tube giving out some ultraviolet light, and then in the what you're seeing there is a drink which has got a chemical called quinine in, and that's fluorescing. Now we're going to see some uranium glass doing the same thing, really quite impressive. So what's happening here is that we're taking ultraviolet light and we're converting it into green light, and that's going to be a kind of crucial concept in how a fluorescent tube works.
So you've got an idea what fluorescence is, and you've got an idea why a fluorescent tube is important. What we're going to do now is put it all together, use the knowledge you've accumulated to explain how these fluorescent tubes work. And there are two main parts of a fluorescent tube. Inside we have mercury vapor. So mercury, as in that silvery metal that runs around, and vapor is being put into a gas state. And it's quite a low pressure gas, and we'll talk about that more later in the video. Around the inside of the tube is a kind of white powder. If you ever look at a fluorescent tube or an energy bulb, they look like they've been painted white on the inside. So that's the fluorescent. So hopefully you've got in your mind that the fluorescent powder, the word fluorescent is something to do with converting ultraviolet light into visible light. Mercury vapor turns out to be very efficient because, and when I say efficient here, one of the benefits of these tubes is that we get a lot of light out for the energy that we put in. An old-fashioned incandescent bulb with a filament, the sort that Thomas Edison kind of invented, produced only 2 watts of light for every 100 watts of energy put in. 2 joules for every 100 joules. So it's about 2% efficient. These are at least 10 times more efficient. So the mercury vapor, we've got electrons going down the tube, colliding with the mercury vapor atoms, causing an excitation. And that de-excitation is releasing ultraviolet light. Okay, so in the tanning context, if you need ultraviolet light, then all you need is a glass tube with the mercury vapor and the voltage to drive the electrons down the tube. But that's not what we want in an ordinary domestic setting, isn't it? What we want is light. So the fluorescent powder on the inside of the tube, and it's also put into washing powder and paper, is converting UV photons into visible light photons. So how does it do that? Well, inside the white powder, we've got substances specially engineered to have lots and lots of close energy levels. So we get an ultraviolet photon coming from the fluorescent tube, so coming from the mercury vapor. That collides with an electron in the ground state of the fluorescent powder and causes an excitation into a higher energy level. And then as that photon returns to the ground state, and this is happening multiple times, as it makes different size jumps, it's giving out different energies of photons. So you can see here I've created a red photon and I've created a blue photon. It might be, and obviously I haven't got the scaling completely right here, it could have been that it had come down through that size jump instead, and we can imagine that being green. So it's all been specially engineered to create visible light. And a word that you'll hear associated with this process is the word cascade. Cascade is a word that usually refers to a waterfall, and we're imagining the electrons jumping down all these steps, randomly taking bigger or larger steps to create visible light. And that's powder all round the inside of the tube as the photons come out, ultraviolet photons come out, creating visible light. It's worth just having a quick look at different numbers of energy levels, or electrons in different energy levels. If an electron goes from n equals 1 to n equals 2, as it comes back down, we've only got one energy level involved. We can only have a single energy of photon involved. However, if we go to the n equals 3, there are now 3 options. We can go all the way from n equals 3 to n equals 1, but we could go from n equals 3 to n equals 2, and then n equals 2 to n equals 1. So that would now mean we have 3 possible energies of photon. If we go, an electron is promoted all the way to n equals 4, it could fall down all the way to the ground state. So that's giving us an extra level. It could fall from n equals 4 to n equals 2. Or it could fall from n equals 4 to n equals 3. And that gives us 3 extra possible energies of photon, plus the 3 that we'd get from when the photon was in n equals 2. So now there are 6 options. And there have been questions that are referred to that. So 2 other things that you're expected to know about the gas inside the tube. The first is that the gas is under low pressure. And the second is that the gas is partly ionized. And we just need to make sure you understand why that is. So gas pressure is caused by particles. And let's try and draw an illustrative diagram to show a difference between low pressure gas and high pressure gas. So if we make the top one our high pressure gas, the particles are considerably closer together. Of course, they're not like a liquid or a solid where they'd be touching, but they're quite close. In our fluorescent tube, we're using low pressure gas, which I'm going to illustrate like that. Now we're going to imagine that we've got the same voltage driving our tubes. And let's just keep it simple. I have 100 volts in each case. You don't need to know the voltage, it's just the idea. Now, if an electron jumps all the way along the whole tube, it gets 100 electron volts of energy. You know that, don't you? I think you can probably see that if it goes 1 centimetre down the tube, and the tube is 100 centimetres long, if it's going a centimetre between collisions, each time it moves a centimetre down the tube, it gains 1 electron volt of energy. In the top tube, the particles are much closer together, so it travels less distance down the tube. So now let's imagine it travels 0.1 centimetres between collisions. So it only gains 0.1 electron volts of energy. So the lower the pressure of the gas, the more energy the electron can gain on average between collisions. And I think typically visible light, we would need more energy. We would need 3 or 4 electron volts. So we'd either need more voltage or even lower pressure. But the key concept is we don't need the numbers. The lower the pressure of the gas, the greater the distance the electron travels between collisions with the mercury vapor atoms, and the further it travels between collisions, the more energy it will have. Finally, we have to ask ourselves, why must the gas be partially ionized? Well, particularly if you study chemistry, you'll understand that our mercury vapor atoms are all neutral objects, aren't they? They've got no charge, and we don't really expect there to be free electrons around in the real world. It turns out that we can get some from our circuit, but basically this is a non-conductor here, so we get a very poor flow of electricity. However, if we can find an electron and it goes herring off down the tube, manages to avoid lots and lots of collisions, and has a high energy collision, say with that atom there, and ionizes it, suddenly we've now got 2 electrons. We had 1 electron before, now we've got the 1 knocked out of that mercury vapor, and they can go steaming off down the tube, either causing further excitations or ionizations. So we need ionization, so we have extra free electrons, free moving electrons, and that allows the gas to conduct. So going right back to the beginning, a fluorescent tube contains mercury vapor. Electrons travel through the gas, causing excitation and the emission of ultraviolet light. A fluorescent powder, by excitation and cascading, converts the ultraviolet light into visible light. The gas is under low pressure to increase the distance the electron travels between collisions, and causing allowing the electron to gain enough energy to cause an excitation, and the gas needs to be partly ionized so it will conduct electricity.